Lehmer's conjecture. Let's begin with something quiet. A whisper from the world of numbers. A question that has gone unanswered for nearly a century. Not because it's too complex to understand, but because the answer simply refuses to show itself. This is the story of Lehmer's conjecture. A small question, buried deep inside the world of polynomials and patterns. A problem so subtle, you could almost miss it. And yet, for mathematicians it's like trying to find the heartbeat of a ghost. To begin this journey, imagine this. A line of numbers, stretching endlessly in both directions. Some of them whole, some of them fractions, some just strange and irrational. Among these numbers, there are certain special ones, numbers that arise from the roots of polynomials, the kind that you may remember from school, equations that look like a series of numbers and powers of x. Now, there's something curious that happens when you look at these roots. You can measure how big they are, not just in the usual sense of size or distance, but in a more delicate mathematical sense called the Mahler measure. Don't worry if you haven't heard that name before. Think of the Mahler measure as a kind of fingerprint for a polynomial. It's a single number, a summary, that tells us something subtle about the behavior of its roots. Most of the time, when the Mahler measure is small, the polynomial is considered simple, and when the measure grows, it often signals something richer, something more tangled, more mysterious. Here's where Lehmer comes in. In 1933, a mathematician named Derek Lehmer was studying these Mahler measures. He noticed something strange. No matter how hard he searched, he couldn't find a non-trivial polynomial whose Mahler measure was very close to 1, but still greater than 1. He found one, though, just one that stood out. Its Mahler measure was slightly above 1, just a tiny bump over that perfect clean number, a quiet imperfection. And ever since that lonely polynomial has stood at the edge, a solitary peak above the number 1. Lehmer asked the question, is there a lowest possible Mahler measure greater than 1? For polynomials that aren't part of a special well-behaved group called cyclotomic polynomials. In simpler terms, is there a floor below which Mahler measures never fall, except when they're part of this well-understood group? Decade after decade, no one has found another example smaller than Lehmer's, and no one has proven that one doesn't exist. It's like standing in a dark forest, hearing a sound just once, and never again. This question, so delicate, so simple, has become one of the great unsolved problems in the world of number theory. And yet, it's not famous like the Riemann hypothesis. It doesn't make headlines or fill lecture halls. It just waits. You might wonder, why do we care about this measure? Why does it matter if there's a smallest one above 1? Well, hidden inside this small question are echoes of many larger themes. Chaos, order, structure, entropy. The same kinds of ideas that guide us through physics, chemistry, even information theory. Lehmer's conjecture whispers across those borders. If true, it would help us understand how polynomials behave, how systems balance, how randomness arises from rules. But there's something else too, something more poetic. You see, mathematics is full of extremes, the highest, the lowest, the infinitesimal, and Lehmer's conjecture is a search for the smallest possible imperfection that refuses to vanish completely. It's like asking, is there a minimum whisper of complexity that cannot be silenced? Many have tried to answer it. Computers have searched through millions of possibilities. Mathematicians have drawn connections to algebra, geometry, and dynamical systems. But the answer never reveals itself. It remains out of reach, not because it's hidden behind complicated equations, but because it's hiding in plain sight. And perhaps that's what makes Lehmer's conjecture so mesmerizing. It's not a towering question. It's not loud or dramatic. It's quiet, almost too quiet. The kind of question you might ask just before drifting off to sleep, eyes half closed, mind drifting. Is there a minimum spark, a whisper of complexity, that echoes louder than silence? Lehmer's conjecture doesn't demand an answer. It simply asks the question, and lets it linger in the dark, a soft question, for a quiet night. The smooth 4D Poincare conjecture. There are problems in mathematics that feel like puzzles. You twist them, turn them, and eventually, the pieces fall into place. But then there are problems that feel like whispers from another world. Quiet riddles that stretch the imagination and bend the fabric of what we think we know. The smooth 4D Poincare conjecture is one of those problems. To understand it, we need to gently step into the world of topology, a branch of math that doesn't care much about size or distance, but focuses instead on shape, connectedness, and structure. In topology, a donut and a coffee mug are the same. That might sound strange, but they both have one hole, one way through. As long as you don't tear or glue, those two objects are topologically identical. Now, within this world of shapes and spaces, there's something special called a sphere. We all know the 2D sphere. It's the surface of a ball. You can draw it, touch it, and hold it. A 3D sphere is a little trickier. It's what we imagine as the outer shell of a four-dimensional ball. We can't picture it directly, but mathematically, it's well defined. Just a step up in complexity. Now imagine a 4D sphere, a shape that exists in 4 dimensions of space. It's not something we can visualize, but we can describe it. We can define it using equations. And we can ask questions about it. Very deep, very strange questions. One such question is, does a smooth 4 sphere have only one smooth structure? Let's unpack that slowly. A smooth structure is a way of understanding a shape where everything can be nicely defined, with no sharp corners, no creases, and no wild behaviors. It's like imagining a perfectly polished marble surface, with not a single scratch or edge. For most shapes in most dimensions, there's only one way to define this smoothness. A smooth sphere is just a sphere, but in dimension 4, something odd begins to happen. Mathematicians discovered that in 4 dimensions, there might be more than one way to make a smooth surface. In fact, there might be many, all different, all smooth, and yet, all topologically the same. It's like finding multiple ways to polish the same sculpture, where each version feels completely different to the touch, but is somehow the same in structure. So the question becomes, is the 4D sphere an exception? In other words, if you have a 4-dimensional sphere, and you smooth it out perfectly, is there just one way to do that? Or could there be hidden versions, other smooth 4 spheres, that are not the same as the original, even though they look identical from a topological point of view? This question is a twist on the classic Poincare conjecture, a famous problem that asked whether any shape that behaves like a sphere is actually a sphere. In 3 dimensions, that puzzle was solved. The answer was yes, and the person who proved it, Grigory Perelman, declined $1 million prize in the process. He simply walked away, satisfied with the work. But in 4 dimensions, we are still not sure. Some progress has been made. Mathematicians have shown that in 5 or more dimensions, the answer is yes, there is only one smooth structure, and in lower dimensions, things are also pretty well behaved. But 4 is special. It's the only dimension where the smooth and topological worlds come apart, where strange new behaviors begin to appear. Mathematicians have even discovered something called exotic smooth structures on 4-dimensional space, versions of smooth 4D space, that are technically different, even though they look the same on the surface. And this leads to a haunting possibility. Could the 4D sphere, this elegant symmetrical object, hide within it countless unseen variations? Could there be infinitely many ways to define smoothness, all coexisting in a realm beyond our visual understanding? No one knows. The smooth 4D Poincare conjecture remains unanswered. Some believe that the answer is yes, that the 4D sphere is unique in its smoothness, and that we just haven't yet found the right tools to prove it. Others suspect that there may indeed be multiple, exotic versions hiding in the shadows of mathematics, waiting to be discovered. And so the question drifts, unresolved, in a quiet corner of mathematical thought. It's not a problem most people have heard of. It doesn't make headlines. But to those who study the deep structure of reality, it is a mystery as profound as any in physics or philosophy. What does it mean for something to be smooth? Can 2 things be the same, and yet not the same? Is reality built from a single blueprint, or do multiple versions exist beneath the surface? These are the questions that make the smooth 4D Poincare conjecture more than just a math problem. It's a doorway into the unknown, a reminder that even the most abstract ideas can hide deep, fundamental truths. And maybe, as you listen to this, you'll drift into dreams where shapes bend and dimensions unfold, and the quiet hum of mathematical mystery rocks you gently to sleep. Noetherian ring classification problem. In the quiet world of abstract algebra, far from the noise of numbers and equations we know from school, there is a puzzle. A puzzle that begins not with a question about how to solve something, but how to describe it. How to truly understand a certain kind of mathematical object. This is the mystery of the Noetherian ring classification problem. Let's start at the beginning. Imagine you're standing in a vast, silent library. The shelves are filled with strange, glowing books. Books that contain rules instead of stories. These are rings. Not the kind you wear on your finger, but mathematical rings, structures built from elements that you can add and multiply, just like numbers, but with their own unique rules. Some of these rings are wild and unpredictable, but others are more well-behaved. These are called Noetherian rings, named after one of the most brilliant mathematicians in history, Emmy Noether. Emmy Noether changed the landscape of mathematics in the early 1900s. She brought structure and elegance to chaos. She showed that in certain mathematical worlds, you could organize things in a way that always leads to clarity. And so, a ring that follows this principle, that doesn't allow infinitely increasing complexity in its structure, is called Noetherian. It's like walking into a room full of tangled wires, and finding out that somehow, each wire is wound up just enough, and no more. There's a built-in order, a hidden sense of limit. So here's the question, the one we still can't answer. Can we classify all Noetherian rings? In simpler terms, can we make a complete list of all the possible kinds of well-behaved rings in the mathematical universe? Can we describe them all in a clean and unified way? Can we put them into neat categories, with names and labels and rules that never break? It sounds straightforward, maybe even simple. After all, if these rings are tame, shouldn't they also be understandable? But that's where the puzzle begins. You see, Noetherian rings pop up everywhere. In number theory, in geometry, in physics. They lie at the foundation of algebraic geometry, which is like drawing with algebra instead of ink. Every time you draw a curve with an equation, somewhere behind the scenes, a Noetherian ring might be whispering the rules. And yet, despite how often we see them, despite how deeply we rely on them, we still can't fully classify them. It's as if we keep seeing glimpses of familiar faces in a crowd, but the full picture always stays just out of reach. Some classes of Noetherian rings are well understood. For example, polynomial rings, which are like the algebraic versions of simple equations, behave nicely. Their structure can be studied, their behavior predicted. But as we try to stretch our understanding further, into more complex shapes and higher dimensions, things become uncertain. There are Noetherian rings that follow all the basic rules, yet refuse to reveal their deeper secrets. Some seem to carry traces of strange geometry. Others seem built from shadows of higher structures. No single theory seems to capture them all. Mathematicians have tried to classify these rings in many ways. By looking at their dimensions, their modules, their ideals, by using tools from logic, topology and geometry. But each time we find a pattern, we also find exceptions. Each rule brings a new layer of mystery. The problem isn't just technical, it's philosophical. Can all structure be classified? Can all well-behaved things be named? Can we ever reach a point where we can say, here is the complete list, here are all the possibilities, there is nothing left to find? Or is there always more? Always a new corner of the landscape we haven't explored? This is what makes the Noetherian ring classification problem so haunting and so beautiful. It's not just a question about rings, it's a question about knowledge, about limits, about whether the universe of mathematics is in some sense knowable in full, or whether it stretches endlessly, like a quiet night sky filled with stars we'll never name. And so the problem remains open, silent, waiting. Maybe one day someone will find the key. Maybe a new perspective will reveal the hidden order behind the curtain. Or maybe, this is one of those mysteries that exists not just to be solved, but to remind us of the wonder of not knowing, of the beauty in the search itself. After all, Emmy Noether didn't seek fame. She sought truth, structure, elegance. And in doing so, she left behind a question that still calls to us, like a soft echo in the halls of mathematics. Can we truly classify all Noetherian rings? Maybe, maybe not. But even in that uncertainty, there is peace. The lonely runner. Imagine you're standing on a circular track. It's a quiet morning. The air is still. The track loops endlessly around you, smooth and perfect. You're not alone. There are other runners here, each starting from the same point, each moving at their own steady pace, none of them turning back, none of them stopping. And then, a question arises, a curious, almost poetic question. Will every runner eventually be alone? This is the essence of something called the lonely runner conjecture, a simple but deeply mysterious puzzle from the world of mathematics. It's a problem that's been passed quietly from one curious mind to another since the 1960s. It sounds easy enough to understand, but no one, not even the best mathematicians, has ever fully solved it. Let's take it step by step. Imagine there are two runners on the track. One runs faster than the other. As time passes, the faster one pulls away. Eventually, the two are on opposite sides of the track. That's a moment where the slower runner is exactly halfway around the circle from the faster one. At that point, they're as far apart as they can be on a loop. You might say, for just a brief moment, the slower runner is lonely. Now add a third runner, then a fourth, a fifth, and more, all running at their own constant speeds. The rule is they all start at the same place and time, but no two runners share the same speed. Everyone is unique. So we ask again, will each runner at some point be at least a certain distance away from every other runner? Will there be a moment when they are truly alone? That's the lonely runner conjecture. More precisely, it says that if there are no runners on a circular track, each with a different constant speed, then each one of them will, at some point, be at least 1 n units away from all the others. Not forever, not always, just for one small moment in time. It's a beautiful thought, a kind of quiet justice for each runner, that in the middle of the chase, the passing, the pacing, each will find a moment of solitude. So far, it's been proven for small numbers of runners, 2, 3, even up to 7. But beyond that, the mystery grows. No general proof has yet been found. No simple explanation has emerged. It just continues to resist. Why is this so difficult? The problem seems innocent, almost playful. It doesn't involve complicated equations or abstract theories. All it asks is whether, eventually, everyone gets a little space. But the challenge lies in the details, because while the idea is simple, the math underneath is quietly intricate. You're not working with straight lines or simple intervals. You're working with time and distance on a circle, with motion that never ends. The runners don't pause. The track never changes, and yet their positions are always shifting. For each runner, the question becomes, is there a time when I'm far enough from everyone else, no matter how fast or slow they are? Mathematicians have tried everything: algebra, geometry, number theory, even computers, to track the runners, predict their positions, and find patterns. But the proof for the general case continues to elude us, and maybe that's part of the charm. The lonely runner conjecture has become more than just a problem. It's a metaphor, a story, a reminder that sometimes, even in a world full of movement, speed, and noise, each of us needs, and perhaps inevitably finds, a moment of distance, a moment of stillness, a moment to be alone. You can almost imagine the runners, circling quietly in the early dawn, no one bumping into another, no one lost, just movement and rhythm. And then for one heartbeat, one runner looks around and realizes, no one is near. For that instant, they are alone with their thoughts. The track belongs only to them. Then the moment passes, the others draw near again. The dance continues, but that memory, that single private breath, remains. So the lonely runner conjecture waits, not because it's forgotten, but because it's timeless, unrushed. It invites us not to conquer it, but to understand it, to sit with it, to reflect. Will every runner find their moment of solitude? No one knows, but the question lingers, quiet, endless, moving in circles, just like the runners. Sensitivity conjecture. You're staring at a row of tiny lights, some glowing, some dim. Each light represents a bit, a 1 or a 0. The most basic building blocks of computation. Behind these bits lies a hidden rule, a Boolean function. It's a kind of machine that takes in all the lights, reads their pattern, and gives you just one answer in return. A yes or a no, a 1 or a 0. Now imagine flipping just one of those lights. One tiny change, one bit switched from on to off, or off to on. And then, something curious happens. The answer from the machine changes. That one flip causes everything to turn upside down. The function, once saying yes, now says no. But sometimes, that flip changes nothing. You toggle a bit, and the machine stays silent, unchanged, as if that tiny difference didn't matter at all. This quiet game of flipping bits lies at the heart of something called the sensitivity conjecture, a beautiful, unsolved mystery in theoretical computer science. It asks a question that sounds so simple on the surface, but reaches down into the deepest layers of how we think about logic, complexity, and the nature of information itself. How sensitive is a Boolean function, really? Let's slow down and think about what we're asking here. A Boolean function is just a rule, a logical decision, that takes in some combination of ones and zeros, and gives you an answer. It might take in 3 bits, or 30 bits, or 300. The more bits you give it, the more complicated it can be. These functions live in the realm of digital logic, and we use them in everything from computer processors to search algorithms. But complexity doesn't always come from size. Sometimes, it comes from sensitivity, from how a function reacts to small changes in its input. If you flip just one bit of input, does the output change? Does the function notice, or does it stay the same? If a function reacts strongly to just one flip, we say it is sensitive. If it takes many flips to make a difference, we say it is stable. Simple enough. But here's where the mystery begins. Over the years, researchers have developed many different ways to measure complexity in Boolean functions. Sensitivity is one way, but there are others, like block sensitivity, where we flip whole groups of bits, or decision tree depth, which tracks how many steps it takes to reach an answer. Most of these measures seem to follow similar patterns. If one measure is high, others tend to be high too. If one is low, the rest are usually low. It's like they all whisper secrets about the same underlying structure, except sensitivity. Sensitivity has always seemed different, more fragile, more unpredictable. The sensitivity conjecture was born from this puzzle. It asks, is sensitivity truly different, or is it secretly linked to the other measures after all? Specifically, it asks whether sensitivity is always at least loosely connected, mathematically, to block sensitivity. Could we find a formula, or at least a bound, that ties them together? Something that proves, if a function has high block sensitivity, it must have high sensitivity too. For decades, the answer to this question remained hidden. Mathematicians and computer scientists searched, poked, and prodded. They found examples of functions that broke patterns, that had low sensitivity but high complexity in other ways. And yet, no one could prove, or disprove, the conjecture. It lingered like a whisper, a riddle. Why should this matter though? Why spend so much time wondering about how sensitive a function is to one bit? Because at its core, this question isn't just about logic, it's about fragility, about how systems respond to change. In a world of computation, where we flip bits and toggle states billions of times per second, knowing how sensitive a process is or isn't, tells us something vital. It tells us whether the systems we build are delicate or robust. In 2019, after more than 30 years, the sensitivity conjecture was finally proven, by Hao Huang, in a paper just a few pages long. The proof was elegant. It used tools from a completely different branch of mathematics, spectral graph theory, to solve a problem that had resisted all attempts for decades. It was a reminder that in math, as in life, sometimes the solution lies not in staring harder at the problem, but in seeing it from a new angle. Yet, even though the conjecture has been resolved, the spirit of it remains. The question of sensitivity continues to inspire new problems, new directions, and new ways of thinking about computation. How much does one small change matter? It's a question that extends far beyond the realm of mathematics, into algorithms, into systems, into lives. And perhaps that's the most beautiful part of all. A single bit, a single choice, can sometimes change everything. So the next time you think of complexity, of chaos, or of logic, remember the sensitivity conjecture, and let your thoughts drift, like a single flipped bit, into the calm, mysterious logic of the unknown. Jacobian conjecture. Imagine a world made entirely of equations. Not wild, complicated equations, but simple ones. The kind you draw on graph paper. A neat line here, a smooth curve there. In this world, math feels like a quiet walk through a peaceful garden, orderly, elegant, and predictable. But even here, mysteries exist. And one of the deepest mysteries, quietly waiting in this garden of equations, is known as the Jacobian conjecture. It begins with a simple idea transformation. You can think of it like stretching or twisting space using math. Picture a soft rubber sheet. You press your hands into it, and the shape shifts, but the sheet remains smooth, connected and whole. In math, this kind of transformation is described using something called a polynomial mapping, a way of transforming space using equations that are made only from powers and sums. No divisions, no square roots, no strange functions. Now here's the question. If you transform space using only nice smooth polynomial rules, and that transformation doesn't squish anything down to a point, or tear anything apart, can you always undo it? Can you always go backward? That's the heart of the Jacobian conjecture. To explain it more gently, when you change one space into another using equations, there's something called the Jacobian determinant. Think of it as a number that tells you whether your transformation is smooth and reversible at a certain point. If the Jacobian is never zero, if it's always a constant number, it means the transformation is locally behaving nicely. No tearing, no folding, no shrinking to nothing. So the big, beautiful question is this: if the Jacobian is always a non-zero constant, can we always find a way back? Is the transformation always globally reversible? In other words, if we know the math behaves well in every small patch of space, can we be certain it behaves well everywhere? It sounds simple, even obvious, and yet, no one has ever been able to prove it. Not in full, not in every case. The Jacobian conjecture was first posed in 1939 by a mathematician named Otto Heinrich Keller. Since then, generations of mathematicians have chipped away at it. They've proven it in some special cases, for low dimensions, or specific types of equations. But the general case, the full final answer, remains out of reach. Why is this problem so difficult? Well, one reason is that local behavior doesn't always tell you the whole story. Just because something looks good up close doesn't mean it works at the scale of the entire universe. It's a little like zooming in on a painting. Every brushstroke might be smooth and perfect, but when you step back, the image might twist or loop in ways you didn't expect. And in mathematics, space can behave strangely when it's stretched by the rules of algebra. Some equations, even very simple ones, can create wild, tangled effects when applied across the whole plane. What looks harmless up close might create chaos when repeated or extended. The Jacobian conjecture asks us to trust the local signs, to believe that if every small piece works, then the whole map must work. But proving that, beyond all doubt, has turned out to be deeply elusive. Over the decades, the problem has touched many branches of math, algebra, geometry, logic, even physics. It's connected to how we understand space, symmetry, and structure. And like many deep problems, it's deceptively simple to state, but profoundly difficult to solve. Imagine being lost in a maze, but at every intersection, the path forward looks perfectly clear. The Jacobian conjecture asks, if every turn looks right, does that mean the entire maze will lead you back home? It's a question that whispers rather than shouts, a question that waits patiently in the background of mathematical thought, quietly challenging our assumptions. And perhaps that's part of its beauty. Not every mystery in math is loud or dramatic. Some are soft-spoken, like the Jacobian conjecture, resting gently in the middle of familiar concepts, asking quietly whether the world always follows the rules we think it should. Maybe, somewhere out there, a simple insight is waiting to unlock the puzzle. Or maybe the problem will remain unsolved for another 100 years. Either way, It reminds us that even in the most structured landscapes, in a world built entirely from equations, uncertainty and wonder still remain. And as you drift deeper into rest, think of the Jacobian conjecture not as a problem to solve, but as a gentle question from the universe, a reminder that some of the most fascinating mysteries are the ones that seem simplest, yet resist every answer. So sleep well, and let your thoughts wander in that quiet mathematical garden, where equations whisper, and mysteries bloom without end. The Continuum Hypothesis. Imagine a line, a simple, perfect line that stretches forever in both directions. No curves, no breaks, just a smooth, continuous path. Now imagine that line as a way of thinking about numbers. Some numbers are easy to count. 1, 2, 3, 4, and so on. These are the natural numbers, the ones we use to count apples, books, stars. They go on forever. But each one has a place. You never skip one. You never land between them. They're like stepping stones, evenly spaced and predictable. But now, let's turn to a very different kind of number, the real numbers. These are the numbers that live on the number line, and they're everywhere. Between 0 and 1, there are infinitely many. Between any two real numbers, no matter how close, there are always more numbers hiding in between. They fill the line completely. There's no gap too small for a real number to squeeze into. So here's the puzzle, the mystery that has captivated mathematicians for over a century. Are there sets of numbers that are bigger than the set of counting numbers, but smaller than the set of real numbers? This is the essence of the Continuum Hypothesis. It was first posed in the late 1800s by a man named George Cantor. He was one of the first to seriously explore the idea of different sizes of infinity. And yes, in mathematics, some infinities are bigger than others. To him, the natural numbers were the smallest infinity. He called it countable infinity. You could, in theory, count them one by one, even if it would take forever. But the real numbers, they were uncountable. No matter how cleverly you tried to list them, there would always be more that slipped through your fingers. Cantor wondered, is there a size of infinity in between? Something larger than the set of all counting numbers, but not as large as the uncountable flood of real numbers. It's an innocent-sounding question, but it has led to one of the deepest puzzles in all of mathematics. Some sets seem promising. For example, the set of all numbers you can write down using fractions, like 1/2 or 2/3. This set is infinite, but it turns out, it's still countable. It's not big enough. What about the irrational numbers? Or the algebraic numbers? Mathematicians tried and tested many ideas, but nothing quite fit in between. In 1900, the great mathematician David Hilbert listed the Continuum Hypothesis as the very first of his famous 23 unsolved problems, a list that would shape the direction of mathematics in the 20th century. But as years passed, the mystery only deepened. In the mid-1900s, two brilliant minds, Kurt Gödel and Paul Cohen, approached the problem from opposite directions. Gödel showed that the Continuum Hypothesis could not be disproven using the standard rules of mathematics. That means, if you assume it's true, nothing breaks. Everything still works. Decades later, Cohen showed something equally astonishing. The hypothesis could not be proven either. If you assume it's false, that works too. Mathematics keeps going. In other words, the Continuum Hypothesis is independent of our current system of mathematical rules. It's like a doorway that leads to two equally valid worlds, one where the hypothesis is true, and one where it's false. So where does that leave us? It leaves us with a puzzle that may not have a single definitive answer, not because we haven't found it yet, but because no such answer exists within our current understanding. To some, this is unsettling. In a field built on logic and precision, the idea of an undecidable question feels almost wrong. But to others, it's a sign of something beautiful, a reminder that even in mathematics, the most exact of sciences, there are shadows and open spaces, places where wonder still thrives. The Continuum Hypothesis asks us to think about infinity not as a single thing but as a landscape, a vast strange territory with unexpected layers, countable infinities, uncountable ones, and maybe, just maybe, something in between. It's a question with no clear answer, and maybe that's the point. As you rest tonight, imagine a line filled with numbers. Some you can count, others you can't, and in the space between them, an unknown. A gentle mystery, soft, persistent, and infinite. The Birch and Swinnerton-Dyer conjecture. Imagine a curve, not one you draw with a ruler or compass, but a curve that lives in the abstract world of numbers. This curve isn't just a shape, it's something called an elliptic curve, a gentle looping path made up of all the points that satisfy a special kind of equation, and it carries within it a secret. A question. One of the greatest unsolved problems in all of mathematics. It's called the Birch and Swinnerton-Dyer conjecture, a name that feels a bit like a spell, and in many ways it is. The story begins in the 1960s, at the dawn of a new age in number theory. Two British mathematicians, Brian Birch and Peter Swinnerton-Dyer, were exploring elliptic curves. These are not exotic shapes in the sky, or elegant spirals you see in seashells, but instead, quiet patterns hidden in the arithmetic of numbers. Elliptic curves have a strange kind of symmetry, and more than that, they have a group of rational points where both x and y are fractions or whole numbers, that seem to behave in mysterious structured ways. The big question was, how many of these rational points are there? Could there be infinitely many, or only a few? For centuries, mathematicians had been fascinated by this very question. Some curves have no rational points at all. Others have a few, and some, somehow, have an infinite number. But predicting this behavior wasn't easy. There was no map, no guide. That's when Birch and Swinnerton-Dyer noticed something strange. They began using one of the earliest computers at Cambridge University to look at hundreds of elliptic curves. And while studying them, they found a connection, a subtle pattern between the number of rational points on a curve and something else entirely, a special kind of function called an L function. An L function isn't like the functions you might learn in school. It's a more complex object, deeply tied to the behavior of prime numbers and the deeper structure of arithmetic. What they observed was this. When the L function of a curve approached zero in a very specific way, it seemed to signal that the curve had more rational points. And when it didn't approach zero, the rational points seemed to be fewer. They wondered, could the exact way the L function touches zero somehow predict the number of rational solutions on the curve? This idea became the Birch and Swinnerton-Dyer conjecture. At its heart, the conjecture says something simple, and yet incredibly profound, that the behavior of this special L function at a single point, a delicate moment on the number line, holds the key to the entire arithmetic of the curve. Think of it like this. Imagine standing at the edge of a vast forest, unable to see what lies beyond, but someone hands you a map, not of the forest itself, but of the winds that pass through its trees. And somehow, by understanding those winds, you can tell where the paths lead, where the streams run, and whether there's a hidden clearing inside. That's the power of this conjecture. But here's the thing. Despite decades of effort, no one has been able to prove it. Not fully. Not yet. Parts of it have been shown to be true in very specific cases. And some of the greatest minds in mathematics, people who have devoted entire lifetimes to the study of elliptic curves, have made progress. But the general case, the full picture, remains just out of reach. And the stakes are high. The Birch and Swinnerton-Dyer conjecture is one of the 7 Millennium Prize problems, a list of the most important unsolved problems in mathematics, each carrying $1 million reward for a solution. But more than the money, it's the mystery that draws people in, because to understand this conjecture, and to prove it, would mean uncovering a deep link between geometry, algebra, and number theory. It would mean decoding one of the hidden languages of the universe. It would mean that the way a function behaves, something abstract and analytic, could tell us how numbers themselves arrange, group, and reveal their secrets. And so, the question lingers, gently, persistently. Can we really know the rank of an elliptic curve just by studying the quiet behavior of its L function? Is the secret written not in the curve itself, but in the way it echoes through the space of functions? No one knows for sure, but every year, new insights are made, new tools are forged, and slowly, the veil lifts, bit by bit. Until then, The Birch and Swinnerton-Dyer conjecture remains one of the great unanswered questions, a whisper from the realm of numbers, calling out for discovery, not demanding an answer, but inviting us to dream. So, as the night grows quiet, and the numbers begin to fade into thought, remember that not every mystery is meant to be solved quickly. Some are meant to be held, like a warm cup of tea in the dark, comforting, endless, and beautifully unresolved. The Navier-Stokes equations are one of the most important sets of equations in all of science. They describe something we experience every day, but often take for granted: the movement of fluids. When we talk about fluids, we're talking not just about water, but also air, even clouds and blood. The way they swirl, bend, ripple, and crash, it's all described, with astonishing detail, by the Navier-Stokes equations. These equations are a cornerstone of physics and engineering. They're used to model ocean currents, weather patterns, the lift on airplane wings, and even the flow of oil underground. But despite how useful they are, we still don't fully understand them. And that brings us to one of the most mysterious unsolved problems in mathematics: the Navier-Stokes existence and smoothness problem. At the heart of the problem is a simple question. When we use these equations to describe how fluids move in 3 dimensions, do their solutions always exist? And if they do, are those solutions always smooth? Let's take a moment to slow down. In math, when we talk about a solution to an equation, we just mean a way of filling in the blanks, a set of values that make the equation true. And when we say a solution is smooth, we mean it doesn't have any sudden jumps, cracks, or infinite spikes. It's gentle, continuous, predictable, like a calm river flowing over stones. Now, the Navier-Stokes equations work beautifully in many situations. They help engineers design bridges that withstand wind. They help meteorologists predict storms. They even help simulate the weather on other planets. But there's a catch. When we push the equations into more extreme cases, when the fluid moves too fast or swirls too tightly, something strange might happen. The equations start to misbehave. They might produce solutions that suddenly blow up, or become infinitely sharp, or vanish entirely. This is what mathematicians call a singularity, a place where the math breaks down, a point where the fluid might in theory move infinitely fast, which of course can't happen in real life. So the big haunting question is this: can these equations produce such singularities in 3-dimensional space? Or do smooth, well-behaved solutions always exist, no matter what? No one knows for sure. And that uncertainty, that single gap in our understanding, is enough to cast a long shadow over entire fields of science. The Clay Mathematics Institute, an organization that promotes deep mathematical research, considers this problem so important that it offers a prize of $1 million to anyone who can solve it. Not because of the money, but because of what such a solution would mean for our understanding of nature. Think of it this way: if the answer is yes, if smooth solutions always exist, then the laws of fluid motion are more predictable than we ever imagined. It would mean that even in the wildest tornado or most chaotic waterfall, there's a hidden order, a mathematical calm beneath the chaos. But if the answer is no, if the equations can break, even once, then we face a deeper truth, that in some places the universe refuses to be described, that even with our best tools, there are storms we may never fully understand. It's worth remembering that this isn't just an abstract puzzle. It touches everything: airplanes, heart valves, volcanoes, hurricanes, ink in water, smoke rising from a candle, every curl, every twist, every splash and spiral, all of it, hanging on whether these equations stay smooth or go wild. Some of the brightest minds have worked on this problem for decades. They've studied it from every angle. They've used computers to simulate billions of particles. They've tried to catch the moment when things go wrong, but the answer still floats just out of reach. It's as if the problem itself is fluid, slipping through our fingers just when we think we've grasped it. And maybe that's what makes it so captivating, because there's something poetic about it, isn't there? That we can write down a few simple lines of math to describe something as complex as the wind through trees, but still not know for certain whether those lines will hold together or tear apart. The Navier-Stokes problem reminds us that nature is both elegant and elusive, that the world we live in and breathe in and swim through is governed by rules we're still trying to understand. P versus NP problem. There is a question in mathematics that lies quietly at the heart of modern computing. It's not loud. It doesn't ask for attention, but it touches almost everything we do in the digital world. From sending an email to unlocking your phone. It's called the P versus NP problem, and it remains one of the most important unsolved puzzles in all of computer science. To understand the mystery, let's start with something simple. Imagine you're solving a puzzle, like a Sudoku. You sit down, pen in hand, and after a little while you've filled in all the numbers. Now imagine someone else walks into the room. They look at your finished puzzle, and they know immediately whether it's correct. They don't need to solve it themselves. They just check it. And that's the key idea behind P versus NP. There are two kinds of problems in this world of computation. The first kind, we'll call them P problems, are the ones you can solve quickly, even as they grow larger. For example, sorting a list of names, or finding the shortest route between 2 points on a map. A computer can do these tasks in a reasonable amount of time, even if the list is long or the map is complex. They're practical, predictable, efficient. The second kind, these are the NP problems, are a little different. They might be hard to solve, taking hours, years, or even centuries for a computer to finish. But if someone gives you the solution, you can check it quickly, like the Sudoku puzzle. Solving it might take time, but checking it, that's instant. So here's the big question. Are those two kinds of problems really different? Or is it possible that every problem where the solution can be checked quickly can also be solved quickly? That's what P versus NP is asking. Is P equal to NP? If the answer is yes, it would mean something extraordinary. It would mean that every problem where you can verify an answer quickly could also be solved quickly by a clever enough algorithm. Suddenly everything would change. Code breaking, scheduling, searching, logistics, security, optimization. Problems we once thought were too large or too messy to solve efficiently might suddenly become easy. What once took years could take seconds. But here's the twist. Most experts believe the answer is no. They believe that P is not equal to NP, that some problems, no matter how quickly you can verify their answers, will always be hard to solve, unpredictably hard, inescapably slow. And yet, no one has been able to prove it. No one has found a problem in NP that can be proven to not have a fast solution. At the same time, no one has found a general method to turn all NP problems into fast solvable ones either. We are caught in the middle, in a kind of mathematical twilight. And while this might seem abstract, the consequences of solving this puzzle are deeply real. If P turns out to equal NP, it could change the world of cryptography. Today, much of our digital security relies on problems that are easy to verify but hard to solve, like factoring large numbers. If someone finds a way to solve those problems quickly, entire systems of digital privacy could collapse. On the other hand, if P truly does not equal NP, and we prove it, then we can rest a little easier. We would know there are boundaries, limits to what computers can do, no matter how powerful they become. Some problems will always resist, some puzzles will always be hard, and maybe that's not such a bad thing. After all, isn't there something comforting about the idea that not everything has a shortcut, that some answers must be earned, slowly, carefully, thoughtfully? The P versus NP problem is more than a technical challenge. It asks us to reflect on what it means to know something, and what it means to find something out. It blurs the line between discovery and verification, between trying and checking. And as we drift deeper into the night, with thoughts swirling softly like wind over still water, we can let go of needing to solve the problem. We can simply sit with it, feel the mystery, admire its shape, because sometimes in mathematics, as in life, the beauty lies not in the answer, but in the question that refuses to be answered. Hodge Conjecture. You're walking through a perfectly silent landscape. It's not a place made of trees or hills, but one shaped entirely by numbers and ideas. A place where curves and surfaces don't exist in space, but in pure thought. This is the world of geometry. Not as we see it, but as we imagine it. And in this imagined world, one of the most enduring mysteries quietly waits. It's called the Hodge Conjecture. A soft name, but behind it lies one of the deepest unanswered questions in all of mathematics. The Hodge Conjecture begins with a dream, the dream of understanding shapes that exist in higher dimensions. These are not shapes you or I could ever hold in our hands. They live in a universe far more abstract than anything in the physical world. But despite their invisibility, mathematicians believe these shapes follow patterns, beautiful patterns, that might one day be fully understood. To make sense of these invisible forms, mathematicians break them down into pieces. They look at the holes, the twists, the hidden tunnels inside these shapes. They ask, how many different paths can wrap around them? How many loops can wind through them? This becomes a way to give shape to the shapeless, by counting the invisible structure underneath. These invisible features are described using something called cohomology, a method of studying shapes by their internal structure. Think of it as a kind of fingerprint for a shape. Every abstract shape has one, and it helps mathematicians classify and compare them. Some of these fingerprints are simple, others are intricate, like a snowflake under a microscope. Now, here's where the mystery begins. In certain special types of shapes, smooth curved spaces called projective varieties, mathematicians have noticed that some parts of this internal fingerprint, these cohomology classes, seem to come from something more concrete. They seem to arise from actual geometric objects inside the shape, lines, surfaces, curves, real pieces of geometry, even if only in the abstract sense. The Hodge conjecture asks a hauntingly simple question. Are these special fingerprints always coming from real geometric objects? Or in other words, whenever we detect a particular kind of internal structure, a certain pattern in the shape's fingerprint, can we always find a geometric reason for it? A curve, a surface, something tangible in the mathematical sense? If the answer is yes, then the world of abstract shapes becomes more orderly. We could understand them not just through numbers and logic, but through geometry itself. We could trace their patterns back to familiar forms, like circles, planes, or more complex surfaces, even in these higher dimensional worlds. But if the answer is no, then there are ghosts in our geometry, patterns that exist, but have no geometric explanation, structures that we can measure, but never see. The Hodge conjecture, then, becomes a boundary, a line between the visible and the unknowable in mathematics. It might sound like a question only for the experts, for those who speak the language of algebra and topology, but at its heart, the Hodge conjecture is about something deeply human, our desire to understand, to find order, to believe that everything we observe has a reason, that every shadow has a source. Despite decades of effort, no one has yet proven whether the Hodge conjecture is true. Some believe it holds the key to unlocking whole sections of mathematics. Others think it may be too subtle, that our tools, our logic, or even our imaginations, might not be enough. It is one of the 7 Millennium Prize problems, a group of mathematical puzzles so profound that solving even one would be a moment of global recognition, and a $1 million prize. But more than the reward, it is the mystery itself that keeps mathematicians returning to the question. Because in mathematics, an unanswered question is not a failure, it's an invitation, an open doorway into new ideas, new methods, and deeper understanding. The Hodge conjecture reminds us that even in the most logical of sciences, there is space for wonder, that in a world ruled by reason, some mysteries are not only allowed, they are necessary. They are what keep the journey going. And so, this question remains. As you drift into stillness, consider it gently. In a universe built from thought alone, can every pattern be explained? Can every fingerprint lead us back to something real? Or are some truths meant only to be glimpsed, like constellations in a fog, their full shape forever just out of reach? Sleep well, with questions in your mind. Let them wander, let them rest. The answers can wait. Twin prime conjecture. Have you ever thought about how numbers behave? Not just any numbers, but prime numbers. Those strange and beautiful numbers that can only be divided by 1 in themselves. They sit like little islands on the number line, mysterious, scattered, unpredictable. And yet, some of them come in pairs. Not just any kind of pair, but twin primes. 2 prime numbers that are only 2 numbers apart, like 3 and 5, or 11 and 13, even 17 and 19. It seems simple, even innocent. But beneath this simple idea lies one of the greatest mysteries in all of mathematics. The twin prime conjecture asks a question that has never been answered. Are there infinitely many of these pairs? Will we always be able to find another twin prime, no matter how far we go? Let's imagine the number line stretching out before us, endless, infinite. You walk along it, passing the numbers one by one. Some of them are smooth and ordinary, but now and then, you hit a prime, and every once in a while, just occasionally, you find two primes standing side by side, with only a single even number between them. They're like stars in the night sky that appear in pairs, close, connected, silent. We know that the primes go on forever. That much has been proven. There's no largest prime, no end to the line. But do twin primes go on forever too? That's where things get tricky. You might think that if primes never end, then pairs of them shouldn't either. And in fact, the more we've looked, the more twin primes we've found. Huge ones, gigantic ones. So large they stretch over hundreds of thousands of digits, each one whispering that maybe, just maybe, the pattern continues. But mathematics demands more than hope. It asks for certainty, a proof, and no one has ever found one. For centuries this question has remained open. The greatest minds have tried. They've studied how primes are distributed. They've looked for patterns, searched for formulas, followed trails of logic. And while we've gotten closer than ever before, we still don't have a final answer. In 2013, a breakthrough happened. A mathematician named Yitong Zhang showed that there are infinitely many prime pairs, less than 70 million numbers apart. Not quite twins, but close. His work was a moment of light in the darkness. Since then, others have helped push that gap smaller and smaller. Today we believe we're within reach. But the true twin prime gap, the beautiful little 2, still sits just out of reach, still waiting. The mystery continues. What makes this problem so compelling is how simple it is to ask, and how incredibly difficult it is to answer. You don't need to know advanced mathematics to understand it. You just need to understand the number 2. That tiny gap between two primes. And yet, that tiny gap hides a universe of complexity. Why do twin primes appear where they do? Why do they seem to cluster at times and vanish at others? And why can't we prove once and for all whether they go on forever? Maybe it's because the primes themselves are more like a dance than a list. They move with rhythm, with silence, with mystery. They don't follow a simple path. They whisper secrets only the universe seems to understand. And the twin primes, those rare intimate pairs, are among the most beautiful steps in that dance. We may never know the answer. Or maybe one day someone will uncover the final piece of the puzzle. It might come from a spark of insight, or from years of careful, quiet work. Maybe from someone young, just beginning their journey into mathematics. But until then, the twin prime conjecture remains just that, a conjecture. A question without an answer. A lullaby of logic, still unresolved. So as you drift deeper into rest, imagine the number line stretching out to infinity. Feel the quiet rhythm of the primes passing by. And every so often, like a heartbeat, a pair, then silence, another pair, then silence again. Maybe, out there in the endless dark of numbers, twin primes are still waiting, still appearing, still dancing. And maybe, just maybe, they never stop. Collatz Conjecture. Imagine a number, any number you like. It doesn't matter how small, or how large. Just choose a positive whole number. Now take that number, and do something very simple. If it's even, divide it by 2. But if it's odd, multiply it by 3, and add 1. Then do the same thing again. And again, over, and over. This simple process is called the Collatz function. And what's strange, is that no matter what number you start with, it always seems to lead to the same place. Eventually, somehow, you always end up at the number 1. This idea might seem almost too simple to be mysterious. And yet, this puzzle has fascinated mathematicians for over 80 years. It's never been proven, and no one knows why it works, or even if it works for every number. This is the Collatz conjecture. Let's take a small number to see how it behaves. Let's start with 6. 6 is even, so we divide by 2. That gives us 3. 3 is odd, so we multiply it by 3, and add 1. That's 10. 10 is even, divide by 2. That's 5. Now 5 is odd, multiply by 3, and add 1. That's 16. Then 8, 4, 2. And finally, 1. Once you reach 1, you fall into a loop. 1 becomes 4, 4 becomes 2, and 2 becomes 1 again. A small cycle that repeats forever. But that's just one number. What happens if we try a larger one? What about 27? It takes 111 steps to reach 1. The numbers jump up and down, rising as high as 9,232, before finally falling down to 1. Yet, it does fall, eventually. People have tried this with computers for billions, even trillions of numbers, and still they always come back to 1. No exceptions have ever been found, and yet, no one can prove that every number does this. That's what makes it a conjecture, not a theorem. A conjecture is something we believe is true, but haven't been able to prove. The rules of the Collatz function are easy to understand, so easy that a child could follow them. But the pattern, the logic behind why it always returns to 1, remains a mystery. Why should something so chaotic, something that can climb into the thousands or millions, always find its way back to the humble number 1? No one knows. The mathematician Lothar Collatz proposed this idea in 1937, and ever since, it has resisted all attempts at a solution. Some of the greatest minds in mathematics have looked at this puzzle. They've tried using number theory, algebra, computation, probabilities, but still, the deeper they look, the more it slips away. Paul Erdos, one of the most prolific mathematicians in history, once said, "Mathematics is not yet ready for such problems." So we are left with a question that is simple to ask, but impossibly hard to answer. Will every positive number always reach 1, or is there a number out there, a strange number hiding in the vastness of infinity, that does something different, one that never settles down, one that keeps bouncing forever, never falling into the cycle? We don't know, and maybe we never will. The Collatz conjecture sits at the edge of what we understand and what we don't. It's a reminder that math isn't just a tool, it's a universe of patterns and possibilities. And some of those patterns remain hidden, not because they are too complex to grasp, but because they are hidden in plain sight, like a whisper beneath a roar. There is something oddly beautiful about the Collatz journey, a chaotic dance that always returns to peace, like a river that twists and turns, crashing over rocks, surging through rapids, but always finding its way to the sea. You can try it for yourself. Pick any number, 7, 15, 82, 913. Follow the steps. Odd, multiply by 3, then add 1. Even, divide by 2. Keep going. Watch the numbers rise and fall like waves, and in time, you'll return to 1, always 1. Unless, of course, there is a number out there that refuses. A rebel, a ghost, a secret hiding in the infinite sea of digits. Maybe it's out there, waiting to be discovered. Or maybe, the answer lies not in the destination, but in the journey itself. So for now, we watch, we wonder, we ask the question again, will every positive number always reach 1? And in that question, we find mystery, we find beauty, we find silence, and maybe, as we drift towards sleep, we find peace in knowing that even the simplest puzzles can hold the deepest secrets. Goldbach's conjecture. Goldbach's conjecture is one of the oldest unsolved problems in all of mathematics. It's a simple question. And yet, after nearly 3 centuries, no one has been able to prove whether the answer is yes or no. The idea came from a letter, written in the year 1742. A German mathematician named Christian Goldbach wrote to the famous Leonhard Euler. In his letter, Goldbach proposed something curious about numbers, specifically, about the numbers we call even, and the numbers we call prime. An even number is any number that can be divided evenly by 2, 4, 6, 8, 10. These are all even numbers. They're familiar, comfortable, and predictable. Prime numbers are a bit more mysterious. A prime number is a number greater than 1 that has no divisors except 1 and itself. 2 is the smallest prime number. Then comes 3, 5, 7, 11, and so on. As the numbers get larger, prime numbers become more spread out, more rare, and more unpredictable. Now here's what Goldbach suggested. Take any even number greater than 2, and you should be able to write it as the sum of 2 prime numbers. That's it. That's the entire idea. For example, 4 is 2 plus 2, 6 is 3 plus 3, 8 is 3 plus 5, 10 is 5 plus 5, or 7 plus 3, 12 is 7 plus 5. It works again and again. You can try it with 20, or 50, or 100. Pick any even number, and it seems that somehow, 2 prime numbers will always add up to give you that result. This idea, this pattern has been tested for even numbers in the thousands, millions, even into the trillions. Computers have checked countless examples, and every time the pattern seems to hold. But here's the catch. No one has ever been able to prove that it works for every even number, and until someone can, the question remains unsolved. Goldbach's conjecture is not a question about just one or two special numbers. It's a question about infinity. It's about whether this pattern, this beautiful dance between primes and even numbers, continues forever. Whether it holds not just for the numbers we can see or calculate, but for all the numbers beyond, out into the endless landscape of mathematics. And proving something for infinity is never easy. What makes this problem so interesting is how simple it is to understand, and yet how resistant it has been to every mathematical attempt to prove it. Some of the most brilliant minds in history have tried. The best computers have searched for counterexamples. None have been found. Still, the proof remains out of reach. It's like walking along a trail that stretches into the distance. With each step, each number you check, you find the same result. Another even number, another pair of primes. Over and over. The path looks safe, it feels reliable, but no one knows whether it continues forever, or whether somewhere far beyond where we can see, the path suddenly disappears. And so the question lingers. Why does this pattern work? Is it a deep truth about the structure of numbers? Or is it just a coincidence that has tricked us across the ages? There are many theories, many ideas. Some mathematicians think a proof must exist, hidden behind a wall we've not yet cracked. Others believe that a counterexample might be waiting out there, among the numbers too vast for our minds or machines to reach. And perhaps that's what makes Goldbach's conjecture so strangely soothing. It's not just a riddle, it's a mystery with infinite steps. Each new even number is another invitation to explore. Each pair of primes is another whisper of a secret that may never be fully revealed. What's comforting is that you don't need to solve it to enjoy it. You don't need to be a mathematician. All you need is curiosity. You can play with the numbers, add them, rearrange them, see how they fit together. It's a puzzle that welcomes you in, and then gently slips out of reach. Maybe that's the charm, that even in something as exact as mathematics, there can still be questions without answers, patterns without conclusions, beauty without certainty, and maybe, as you drift off to sleep, you can imagine those even numbers stretching out into the stars, and the prime numbers quietly pairing up beneath them, dancing in harmony, endlessly, silently, just out of reach. And whether Goldbach's conjecture is true or not, the wonder it inspires will always remain. The Riemann hypothesis is one of the greatest unsolved mysteries in mathematics. It begins with something surprisingly simple, the idea of counting prime numbers. Primes are the building blocks of all whole numbers, numbers that can only be divided by 1 and themselves. We can list them easily: 2, 3, 5, 7, 11, and so on. But the deeper question is, how are they distributed across the number line? In the 1800s, a German mathematician named Bernhard Riemann studied this question. He noticed a pattern, something hidden beneath the surface of the primes. To explore it, he used a strange, beautiful function called the Riemann zeta function. This function takes in complex numbers, numbers that include both real and imaginary parts, and produces surprising results. At first glance, it might seem abstract or even strange, but within it lies a possible answer to the age-old question: how are the primes arranged? Now here's the heart of the mystery. The Riemann zeta function has what are called zeros, points where the function equals 0. Some of these are easy to find, but the truly mysterious ones are called non-trivial zeros. They don't lie on the obvious places, they lie deeper, hidden in the complex plane. Riemann made a bold claim that all of these non-trivial zeros fall on a single line, a perfectly straight vertical line, known as the critical line, where the real part of each input is exactly 1/2. This might sound technical, but think of it like this. In a vast sea of numbers, Riemann believed the hidden structure of the primes was whispering from a single invisible thread. And if every non-trivial zero truly lies on this thread, then we can understand prime numbers in a way never thought possible. But no one has ever proven it, despite over a century of effort, and countless zeros checked by computers, millions, even billions. Not one has been found off the line. Yet still, the proof remains elusive. Why does it matter? Because if the Riemann hypothesis is true, then the secrets of the primes are more orderly than we imagined. It would bring stability to many areas of mathematics, from cryptography to chaos theory. And if it's false, then the number system might be far more chaotic, more unpredictable than we dared to believe. The Riemann hypothesis sits quietly at the crossroads of certainty and mystery. It has not been proven, nor disproven. It simply waits, like a puzzle left on the table, just out of reach, tempting every curious mind to try, and try again. Perhaps, as you close your eyes tonight, imagine a silent line stretching across an infinite plane, and imagine numbers dancing around it, always just a little out of focus. Not everything in the universe needs to be solved. Some ideas, like this one, exist simply to remind us of how much more there is to know.